Okay, so the title for this lesson is 11.1, and these are solving systems of equations. Systems of equations. And these are in two variables, which is different than what we're headed to next week. We'll have three variables. So I think the first thing we need to do is we need to define a system. Notice that it says systems of equations, plural. So a system of linear equations, what do you think? Consists of a system of linear equations consists of what? Two or more equations. Good. And if it's in two variables, this is going to be two or more equations made up of two or more variables. A system of linear equations consists of two or more equations made up of two or more variables. This is one of those topics I've told you before, whether or not they're important moving forward. This is one that you're going to use again and again and again. It's so important that you can solve a system of equations. We use it in pre-cal. We use it in calculus. Those of you that are not headed in that direction, I have some kiddos that are in a circuits class right now, and they use solving systems nearly every day while they're trying to figure out their circuits. So it's an electricity thing. It's everywhere. It's everywhere. This one's important. You can look at this. This is a system of equations. This is an example. A lot of times we'll see a system with a bracket or a big brace like this. That helps you know what equations are involved in the system. It just kind of helps you group them together. This particular example has 2x plus y equals 15. And then 3x minus y equals 5. This is a set of equations, also known as a system. My old textbook always put this bracket thing out in front. This textbook never puts it. So, whether or not you see that, I don't know. Sometimes you do, sometimes you don't. What do you call it when you find the answer? What's the word? The solution. Okay. So the solution to a system of linear equations in two variables. So I'm just going to say the solution to a system in two variables is the ordered pair that satisfies both equations. The solution to a system in two variables is an ordered pair that satisfies both equations. An ordered pair. So it's a location thing. It tells you what x and y are that would make both of these equations true. Thank you. All right, so the solution to this set is 4, 7. 4, 7. We're going to test it and see that that is true. By the word satisfies, that means makes equations true. It's got to work. It's got to work. So 4, 7. How do you think we're going to test it? Plug it in. Plug it in. It's got to make both equations true. So for x, I'm going to put 4. And for y, I'm going to put 7. So on the top equation, I've got 2 times 4 plus 7. It's 8 and 7. 15. So that one is true. It works. But for it to be the solution, it's got to work on both equations. So 3 times 4 minus 7 is 5. What's 3 and 4? 3 times 4 is 12 minus 7? 5. So you can see that 4 comma 7 is the solution that makes both of these true. Okay. I just gave you that solution. What we're going to be working with today is how to find that solution. Okay. So what I want you to do right now is consider the following picture. There are types of linear systems. Okay. Sometimes you get exactly one solution, in which case the system is called an independent system. That has exactly one intersection. You can find it, okay? That's going to look like the first picture. The second type of system is an inconsistent system. It has no solution. Why would it have no solution? Because they don't intersect. Why would they not intersect? Because they're parallel. The lines are parallel. And then the last kind would be a dependent system. This one has infinitely many solutions. Why would that be the case? They're on top of each other. It's the same line twice. Okay? In this case, it says every coordinate pair on the line is the solution to both equations. The lines are coincident, meaning they happen at the same time in the same place. All right? I want you to get this picture kind of written down in your notes somehow, and you can summarize. You could just draw the 3 graphs and kind of jot down what they mean, but I want this picture in your notes somehow. Deal? 2. This is going to be example 2. I skipped example 1. Example 1 was just proving that a solution works. I think we can do that. Okay, we're going to do that for all of the rest of the problems anyway. So we're going to jump straight into example 2. This one, it says solve by graphing. So there are 3 methods that we're going to work through for finding the solution to the system. 3 different methods. The first one we're going to solve by graphing. Then we're going to do solve by substitution. And then we hit my favorite, solving by elimination. Okay, all 3 are useful for different reasons. Graphing is my least favorite. If we had to pick one of the methods to do, I don't like graphing the most. I like elimination. It's faster. But I digress. So our system here says 2x plus y equals negative 8. 2x plus y equals negative 8. And x minus y equals negative 1. So we got 2 different equations here. We're going to solve them by graphing. Solve by graphing. Okay? Which means I got to graph them both. I wouldn't choose this method if I had the choice for this particular setup, because neither one of these graphs or neither one of these equations are in slope-intercept form. I might do graphing on first instinct if they were both ready to graph. We're going to have to do a little work to get them there. And so for that reason, I wouldn't choose graphing if I had the choice here. But who are we? We don't get to choose. So that first equation, it says 2x plus y equals negative 8. 2x plus y equals negative 8. And we want this guy in slope-intercept form so that we can put it on the graph. Which means I'm trying to get it to say y equals mx plus b. So what's my move going to be here? Move the x stuff. I assume that you mean to subtract it because it was a positive 2x. That leaves me with y equals negative 2x minus 8. Y equals negative 2x minus 8. Okay. The other equation said x minus y equals negative 1. We want it to be in slope-intercept form as well, so what are we going to do? Move x stuff. I think we talked about this a lot. And then if there's anything in front of y, a coefficient of y, what are we going to do? Divide by the coefficient of y, which in this case is negative 1, even though I don't see the negative 1. So what's my green equation going to come out to be? y equals x plus 1. Okay, so we've got two equations here. I happen to give you a handy-dandy sticky note that has graph paper on it. So at this point, I would stick that note in your notes because it's a sticky note. No? No? Okay, that's fine. I'm over here. Okay, so to graph the blue equation, we want it in slope-intercept form. We already have it there. So the first thing we're going to do is start at B. Where's B on the blue equation? Negative 8 on the y-axis. So you're going to go down 8 clicks. 1, 2, 3, 4, 5, 6, 7, 8. And I would mark that y-intercept. What's the slope on the blue one? Negative 2. M equals negative 2 over 1. That's a negative line. So what are my options for my slope? I could go down 2, right 1, or what else could I do? Up 2, left 1. Rise and then run. Up 2, left 1. Up 2, left 1. So I have a somewhat neat graph here. Whoa, Pete. Wowzers. That's about the best I'm going to do. Where does my green graph begin? 1, because it says y equals x plus 1, so I know that that B is 1. That's my y-intercept. And then what? It's positive. What's the slope here? M equals 1 over 1, right? Positive rise 1, run right 1. But that's not going to take me toward the other line where I could see where the two lines intersect. So I might not want to keep going up and right. I could go down 1, left 1. Down 1, left 1. Down 1, left 1. There he is. Down 1, left 1. Cool? So finding an intersection using a graph is not a bad option. You need a couple of things. You need your equations to be ready in y equals mx plus b form. It helps if you have a handy-dandy sticky note graph paper, because otherwise you're left to, my graph may not be accurate. My scale may be off and I'm not able to see where these two lines intersect. Okay. Where does yours intersect? Mine is exactly at what? Where is yours? What's your solution? X first? That feels good. Negative 3 and negative 2. That's the solution that I got. Does it work in both places? Go back to these original equations. If I have x is negative 3, then I'm going to have negative 3 for x minus 2 for y. Is negative 6 minus 2 negative 8? Yes. Okay, affirmative. How about on the other one? Negative 3 minus negative 2. Does that make negative 1? No. Plus. Yeah, it does. Negative 3 plus 2, right? That makes negative 1. Okay. So graphing's good. Graphing's especially nice if you have a calculator. If you don't, we need a better option. Okay. So moving on, we're going to go to example 3. Y'all still trucking with me? Everybody okay? All right, so first of all, can we use graphing if the system is Inconsistent, which means the lines are parallel. There's no solution. Could I use a graph to find the solution there? I could look at the picture and see that they were parallel. I could tell that they don't have a solution. Could I use a graph to find a dependent solution or a system of dependent lines? Would I find the solution there? No. I would have to see that I'm graphing the same line twice. Right? Okay, so here's example 3. Before we get to example 3, I want to write some how-to stuff down. Do y'all want the how-to stuff or do you want to just do it? Do you like the how-tos? Okay. All right, so how to solve a system using substitution. And remember, when we substitute, this is like we talked about with the basketball players before. If I sub in for something, I've got to sub what I'm subbing in for out. It doesn't work if I leave the player. I've got to pull what I'm trying to get out first. Okay, so here's our system. We've got solve for one variable. Solve for one variable. Remember, you're going to have at least 2 variables. So you're going to solve for one of them. How I know which one to solve for is I'm always looking for what I call a naked letter. A naked letter. I want to find the variable that looks the easiest to isolate, meaning it doesn't have a coefficient. Look for the naked letter. It doesn't have a coefficient. Once you solve for that variable, you're going to substitute for it. Substitute into the other equation. Substitute into the other equation. Now, your other equation is going to look longer, but it's only going to have one variable. And if you only have one variable at a time, you can solve. Okay, so that's the idea. Step 3, you're going to solve for the other variable. Solve for the other variable. And then what are you going to do after you've solved for your second variable? What does it feel like? Plug it back in. Yeah, so you'll substitute back into the first equation to solve for the original variable. Lots of substituting. Substitute back into the first equation that you used to solve for the original variable. And what's the last thing we want to do? After we think we've got a home run. Plug it in. We want to check. Check your solution. You want to check the solution. You want to make sure that what you think works in both equations. I like substitution. Substitution's a little longer, but I prefer it to graphing. I especially like substitution when it's really obvious what letter I want to use. When I can see the naked letter, I'm pretty much going to go for substitution every time. Are y'all ready for the example? No, not at all. Sorry. I just am so excited. I like this stuff. You're going to like it too. I believe you're going to like it. Good? No? Yes? Yes? Ready? Set? Griselda? Yes? Yes? Okay. Here we go. Example 3. So our system of equations is negative x plus y is equal to negative 5. And the other equation here says 2x minus 5y is equal to 1. And because this method is substitution, that's what we have to use right now. Do you see a naked letter? Yeah, y. That first y in that first equation is all by himself. Can y'all tell that right here? There's not a coefficient. So that's the target. We're going to set the equation equal to y, and then we'll go from there. Okay, so we're going to take our first equation, that negative x plus y, and we're going to solve it for y. What are we going to do to both sides? Plus x. Add x to both sides, she says. Y is going to equal x minus 5. Okay, y equals x minus 5. Now, we have a naked letter. We have solved for that letter. So now we're going to take that stuff into the other equation in place of y. Can you tell? So into my second equation, I'm going to have 2x minus 5, but instead of y, I'm going to open parentheses and put in there x minus 5. Yeah? And why did I do that? Yeah, because y equals x minus 5. And now I have an equation in only one variable. And anytime I'm down to one variable, and some of you are already headed in this direction, you can solve for one variable. So I distributed the 5. It's negative 5, so that makes negative 5x. And then negative 5 times negative 5 makes what? Positive 25. So I kind of made a big uh-oh over here. That should be positive 25 equals 1. Combine like terms. Negative 3x plus 25 is 1. Now what? Minus 25, minus 25. Negative 3x equals, what's 1 minus 25? Minus 24. So I've got negative 3x minus 24, or equals negative 24, divided by negative 3. X is 8. Hey. Now what? I solved for the one variable. I'm going to plug back into the other equation, this one right here, y equals x minus 5. Now I know what x is. X is 8. And 8 minus 5 is 3. So y is 3 and x is 8. What's my ordered pair? What's my solution? 8, 3. And now the last thing we want to do here is check it. Make sure that that 8, 3 works in both places. So I'm plugging into the first equation. Negative 8 plus 3 equals negative 5. True? Yep. Presley gave it a nod. How about 2 times 8 minus 5 times 3 equals 1? What's 2 by 8? Minus 15? Is it 1? Sweet. Very good. Okay. Yeah? Okay. So I'm going to give you a try it for substitution. You got to try it. We've only got about 9 minutes left, so. But I think you're going to like being able to do this. Have y'all done this before? I mean, I know you said you needed a refresher, but have you done the actual substitution method before?
I don't think so.
Don't think so? Okay. It's super handy. We use substitution all the time. All right, so here are your two equations. X is equal to y plus 3. And your other equation says 4 equals 3x minus 2y. And do you see the golden nugget that they laid for you? They set that x equal to y plus 3. You already have a naked letter. This x is already set up, ready for you to drop it right here. Yeah? It's already ready to substitute because they already isolated the x variable. So into your other equation, you're going to be able to write 4 equals 3 times, and instead of x, what are we putting? Y plus 3. And why do we want that? Why is that best? What can we do now? So we can distribute here. 4 is equal to 3y plus 9. See, when we have only one variable, we can handle things. 3y minus 2y makes 1y. 4 minus 9? Negative 5 for y. So what does that mean for x? X is y plus 3. So x must be negative 5 plus 3. X is negative 2. So what's my solution? Negative 2 comma negative 5. Good. And then we want to do what? Check it. Negative 2 equals negative 5 plus 3. I agree. How about 4 equals 3 by negative 2 minus 2 by negative 5? 4 is negative 6 plus 10. Yeah. Yeah, I'm in. Does that wrap us up today? Okay. Just making sure that we got all of the slides. I think it paused periodically, so I'm going to play this. And if you need the extra slides or something happened to the video, you can pause it here and catch those, okay?